Good morning or good afternoon, wherever you may be, East Coast, West Coast. My name is Andy Deal. I'm your host today, and thank you for joining us on this class, which Daniel Nadeau, one of our excellent application engineer, part of our technical team based out of Pennsylvania, will be walking through Simcenter 3D, which used to be called NXCAE, Advanced Simulation. But before I pass the presentation over to Daniel, I do want to remind the audience that at any time if you have questions, please type it into your chat panel and we will address your question in the Q&A portion of the webcast. And also before you log off the webcast, or I'm sorry, after you log off the webcast, there'll be a survey that pop up. It's a very short 5-question survey, take you about a minute to do. Please take time to fill that out. It helps us a lot in terms of understanding whether or not the content was good from your perspective, and it helps us, to work on our end to make sure that we deliver quality and good content for you. So with that, I will pass the presentation over to Daniel. Daniel, all yours.
Thank you for the introduction. Hello and welcome. Today I'm going to be giving an overview of Simcenter 3D. So Simcenter 3D is the, I'll say, replacement for NXCAE. It's just a rebranded name for NXCAE Advanced Simulation. So just get my slideshow here. So here a little bit about myself. My name is Dan Nadeau. I'm an application engineer. I specialize in FEMAP, NXCAE, NXCAD, and NXNASTran. So today we're going to be talking about NXCAE or Simcenter. So that's the agenda. So what is Simcenter 3D? And then I'm going to go through 2 demo models. One's going to be a solid model, and one's going to be a mid-surface model. And hopefully through this presentation I'll be able to show you some tips and tricks and some uses in NXCAE. So here's the new Simcenter portfolio. Today we're going to be talking about the 3D CFD portion of the analysis, and we're going to be primarily focused on the structural analysis. Now, one thing with Simcenter 3D is that now you see that there's a section for testing, so that would be physical testing, and there's 1D simulation as well. So that is the full Simcenter portfolio, and we're going to spend our time talking about the 3D in our webinar today. So here's just the overview of the 3D CFD simulation. We're going to be using NXNASTran as our solver to solve our structural analysis. So here's just the basic file structure for NXCAE or Simcenter. So you have a master part, which would be your CAD model, which would be, the part that is used in CAD to, design, maybe do CAM work later. So this is the master part that would be in your top-level assembly. So us in our FEA world, we're going to take an idealized part. So our idealized part, we're going to remove rounds, fillets, blends, things like that. So we're going to do some model defeaturing with that. And then we're going to create a finite element model, so a FEM part, which controls properties, materials, things like that. And then we're going to create a simulation part. So at the sim level is where we apply our boundary conditions and where we would solve our model. So that's the basic file structure for Simcenter. So here is the idealized part. So this is one of the nice things with using NXCAE is that we can use this idealized part to do multiple what-if scenarios and remove holes and blends and fillets and see how it affects our analysis. We can do simple changes fast and easy and go back into the FEM part with our changes to our idealized part and see these changes in real life. So I'm going to show you that live with a demonstration. All right, so I have just a simple connecting rod, and I'm going to go ahead and do a simple, I'll say, get your feet wet analysis of this connecting rod. So the first thing that we would like to do is launch the application, and it's now called pre-post. So if you select the pre-post, this will bring you into the pre-post processor known as Simcenter. From here, I'm going to create a new fem and sim. So those are those two parts that I just talked about. And inside here, you'll see that I'm creating the fem, the sim model, and I'm associating it to my master part. So this would be a master part that I would grab from, maybe my top-level assembly. Maybe if I'm using Teamcenter or some sort of data management, it's just a way that I can control and use my idealized part as my local editing instead of going ahead and messing with the rod at the top level. So I'm going to create my idealized part. I'm going to use everything visible, but if I, say I was using the assembly, I could go ahead and specify whatever part I wanted out of the assembly to do my FEA analysis. Right now, my solver is specified as NX Nastran. I'm going to do structural analysis. As you can see, we can use multiple solvers to go ahead and solve this, but today we're going to spend our time talking about NX Nastran. So I'll hit OK. And this is just my Nastran options that I can specify, so I'm going to run a Solution 101 linear statics for this analysis. If I ever needed to change, some bulk data case control Nastran information, I could specify that here. Or if I wanted to run a different solution type, I could define the different solution type that I wanted. So if I wanted to run, Solution 101 or anything else, I could specify that. So I'm just going to keep the defaults, and we're going to run this, as a simple get our feet wet model. So if you look down in my left corner, I have my simulation file view. And right now, I'm at the fem level. But as you can see, here is the rod, which is my bottom level of my assembly. So this is where my part came from. And then I created my local idealized part. And then from that, I have my fem and sim model. So what I'm going to do is go to my idealized part and make a simple change to the model. So this just gives me a warning when I pop open, before I modify, I need to promote this. So that's just saying when I edit this model right here at the idealized part, I'm not actually going to mess with the top level rod. So I can go ahead and do a command like idealize geometry after I promote it. I'm going to do this command to idealize my geometry. And maybe I just want to do something as simple as remove the holes. If I wanted to remove blends and fillets, I could do that. I have synchronous technology, and I have the full application of NXCAD to go ahead and do that. So all I did was remove the holes in the model simply and easily. But maybe I wanted to, make some more design changes. I could do that using the simple tools built into the pre-post. But if I wanted to, I could always step out of this application and move right into modeling. And once I get into modeling, I'll have the full suite of NX to make these changes. But for this example, we're just going to do something simple as removing those blends. Those holes, I'm sorry. So let's go ahead and step up to the fem model. Just let me know that I made a change. And let's go ahead and mesh the part. So for this example, I'm just going to throw a 3D tetrahedral mesh on it. And here's where we specify what we want to mesh, and we specify a mesh size. Now I'm just going to give this a uniform size. I'm just going to specify 2 millimeters. I do have some options for my mesh, so I mesh settings, mesh quality, but for this example, we'll keep it simple. And then the one thing that NXCAE or Simcenter does different than a lot of programs is it has a thing called this mesh collector. So I'm going to go ahead and right now it's automatically creating. Let's go ahead and create our own mesh collector. So inside the mesh collector is where I would define the properties, and inside that property is where I define the material. So right here is my mesh collector. I'm creating a 3D solid because I was doing a 3D tetrahedral mesh, and I'm going to create the property as a P solid. As you see, I have other options as well. And inside here, I'm going to go ahead and define my material. So I'm going to hit the choose material, and I'm going to use the material library that's built into it as well. So just going to go ahead and grab steel in this example, but as you can see, this library is a full list of materials. If you wanted to create your own materials, you could create your own materials on the fly. If you needed to use something other than isotropic material, you could define that here as well. So now I'm just going to accept my other defaults, and I'm going to hit OK. So now when I mesh this part, it's going to be that property and that material. So as you can see, the part has been meshed. If I wanted to spend some more time on mesh quality, I could do that. But for now, we'll just keep it very simple. So now that I have the part meshed and I have my 3D collector defined, as my solid, and I have that 3D mesh inside. Let's go ahead and apply boundary conditions. So to do that, we're going to have to step up to our sim model. So inside here, let's go ahead and apply a load. And for this case, I'm going to apply a bearing load at the end of this connecting rod here. And I'm going to enter a value of 1,000 newtons. And for my vector, I'm going to apply it in my minus y direction, or I can use this y-axis button and make sure that I'm applying in the correct direction. As you can see right here, it is pointing in this direction. So now I have my bearing load applied to the end. Let's go ahead and apply a constraint. So for this case, let's go ahead and specify constraint type, and let me pin the internal faces here. And as you can see, once I hit OK, it automatically created a coordinate system for me, so I can do this pin constraint based on that coordinate system. And I need to make sure that the load, the connecting rod continues to go in this minus y sub c direction in my coordinate system. So I'm going to need to apply another constraint just to satisfy Nastran to solve this model. So let's go ahead and specify a user-defined constraint, and I'll just make sure my degree of freedom 1 would be fixed so that the part doesn't move this direction. So I'm going to go ahead and apply it to, I guess, this single point right here. And all that doing is making sure that it stays in that plane. Now, inside our sim model, you'll see I have my constraint. I have my pin constraint. So if I ever needed to go back, say my user-defined constraint,